Hello, everyone. My name is Onkar Dalal, and I head the AI and data science teams at Turing. Today, I'm going to talk about MLOps evolution in a fast growing marketplace. The way we have structured the talk, I'll start with an overview of how we use AI at Turing. Then we'll talk about different stages of MLOps and discuss the problems we are trying to solve. Next, we'll talk about evolution, and we frame it as a 0 to 1 and one to many stages. And we'll talk about each stage of MLOps in this context. We'll also share some learnings and insights that we have got from our internal use cases as well as client case studies. Finally, we'll end with the path forward for enterprises at different ML stages of ML maturity and how to develop further. What is Turing? Turing is a marketplace for world's most deeply vetted developers to get matched with clients. We have 2 million developers on our platform and we are growing 80,000 every month. We are building an AI-first tech services company on top of world's largest talent cloud. We use AI in several components of our marketplace. We use it for generating demand. We use it for building and qualifying or vetting our supply of developers. And we use it for marketplace optimization or matching the developers with our clients. For this talk, I'm going to focus on two main components, that is the vetting and matching engines. Traditional recruiting starts and ends with resume-based interview selection. This leads to a large variance of interview performance of candidates. We have all been in tens of interviews with candidates before finding a good one. To solve this inefficiency, we have built a vetting engine where when a developer starts, we have a very low confidence estimate of their skill levels. But as they traverse through the various stages of our vetting engine, we build a higher and higher confidence of their representation of their skills and their proficiencies. The output of this vetting engine is a deep representation of a developer. We use this proprietary rich information on our developers into the matching engine. This is an ML system designed to search and recommend the most suitable developers of our 2 million developers. This includes matching the technical requirements of the job, the seniority, time zone, as well as prices for the customer's needs. And we do all of this at large scale. We understand and evaluate our developers' experience along different dimensions. We understand different role types, tech stacks, cloud experiences, as well as we gauge their seniority levels. We use multi-format testing to understand our developers' expertise levels in each of these dimensions. We are also integrating GPT-4 to further enrich our knowledge graph, understand our devs' domain experience, industry background from combining structured and unstructured data from the resumes, as well as information of companies and schools at a global scale. Here is a sneak peek of our multi-format testing. We evaluate tech skill fundamentals via multiple choice questions. Here, we aim to maximize the information gain. We use ML models to drive efficiency here. We build models to predict answers of unseen questions. This helps us fill in the blanks in vetting coverage and makes it efficient for our developers to give us the required signals. We are also constantly updating these tests, and we normalize scores for interoperability between these different tests using statistical techniques. We also evaluate our devs through various practical coding challenges. This is where a developer needs to understand a realistic problem and make coordinated changes across multiple files, just like we do in our real jobs. This goes multiple levels deeper than the run-of-the-mill lead code style interview challenges, which we rarely encounter in our day-to-day coding. This also makes our vetting very challenging for models like ChatGPT to beat. At the end of our vetting process, we have a very deep understanding of our developers through their performance in tech skills, their understanding of different technical concepts, their soft skills, and their coding abilities through various practical challenges. We also have an understanding of the traditional features of their past work history, their certifications from resume, LinkedIn, and GitHub. All of these information about our developer becomes the base for the matching engine. This becomes the source for our matching search and recommendation systems to match developers with jobs. Under the hood of our search system, we use BERT-based embeddings to match resumes with prior experience on resumes with the job requirements. We are also experimenting with embedding-based retrieval. The embeddings combined with the proprietary vetting data feed into our multi-stage ranking models. We use GBDT models to predict relevance of a developer to a job, to predict interview success probabilities, as well as predicting developers' interest in a job. The final ranking you see here is a combination of a multi-objective optimization. We have also built ML models to rationalize pricing amongst globally distributed developer pools. We have to factor in local supply and demand of talent, as well as purchasing power parity in doing so. And we have built all these ML models on top of a scalable machine learning infrastructure, which supports various product use cases, A/B testing, and is flexible model types. We also have a robust offline and online inference engine, which is built on top of Vertex AI. So to recap, we combine the traditional resume, LinkedIn, GitHub signals on our developers with our proprietary vetting signals, which we get from our vetting engine on the developer side, and we match them with the structured and unstructured requirements from the client side to make a recommendation. Our matching is so accurate that some of our clients test the model and skip interviewing completely. For those who don't, we also support custom interviews. Our success rate is so high that we offer a risk-free trial, 2 weeks trial for every developer that is hired on our platform. So that goes to show the power of ML powering our platform. So in the next section, which is the meat of the talk, I'm going to talk about what is MLOps. MLOps is a combination of DevOps and ML. It's the application of DevOps methodology and learnings applied to the ML development. It embodies a shift from artisan-like approach to model building and model deployment to an institutionalized way of infusing intelligence into the enterprise. We define MLOps in these 5 stages. The first stage is model development, where we are identifying and building data sources and pipelines to solve a problem. We're also building a model, machine learning model, which includes training, testing, and validation of the hypothesis, as well as making decisions on model complexity. The second stage is model deployment and experimentation. Here, we productionize the model which was learned in the first stage. This includes defining configuration management, versioning, and A/B testing for real production traffic. The third stage is continuous integration and deployment. Here, we focus on building unit and integration tests. We start auto-scheduling the machine learning pipelines, and you want to start refreshing the models which automatically. The next stage is model governance. Here, we build monitoring and triaging of model issues and start thinking about model explainability and responsible AI. The last stage is cost optimization, where we build an understanding of cost with respect to various components of the ecosystem, especially when deployed at scale. And we start thinking about cost versus revenue trade-offs of the entire ecosystem. Here is a famous picture from the 2015 paper, which came from Google. It highlights the tiny component in blue, which is the ML model code, and then the whole set of engineering support system required around it to be able to reliably derive business value out of that ML science component. This goes to show the scale of effort required around the machine learning itself to make it work for the production use case. So the next question is, how do we evolve this? How do we go from this tiny blue square to the entire ecosystem? So we think of these in 3 rough stages in which every company's ML evolution occurs. In the first stage, which we call the crawl stage, the machine learning models are being developed, but they are not being developed, they are not running live in production. So 80% of the models developed in this stage never get to production, which is expected given that at the early stage, you are testing multiple hypotheses and only some of them work. Once we have a successful candidate, we next get into the second stage, which is the walk phase, where we deploy the first model in live production. We get real users and customers to interact with the output of the model. This part is highly relevant for companies who don't have any infrastructure. They need to create everything and get the most promising model in production. That brings us to the third stage, which is the run stage, where we scale our ML practice to have many models, support many products, and have multiple collaborators. This is relevant for enterprises that have already built some models in production, but they don't have things working very well, or things are hard to control and messy. Most companies invest in some infra, but there are different parts of it are in different levels of maturity. Now, as you can imagine, the business value only comes from the later two stages. The initial stage is a lot of investment, which is net negative in terms of business value. So MLOps is a paradigm. It's a set of tools, skills, and concepts that get us there. So let's discuss what we learned from our own experience and from our customers about how to focus on and avoid some of the pitfalls in this landscape. So we think of our evolution in two stages, a 0 to 1 and 1 to many, and highlight the dependencies and challenges in each stage. These stages are deeply interrelated. If you fail in the 0 to 1 stage, then the 1 to many stage may not come at all. If you don't balance the investments in good infra design and value delivery in the 0 to 1 stage, then more often than not, we have to pay huge costs in the future for building the right foundation for the 1 to 1, 1 to many stage. This often becomes a bottleneck and in drawing value from scaling the machine learning teams. We can hire a lot of data scientists, but the infra challenges usually bog teams down. In the initial phases, companies usually follow the paradigm of let's train the model and we'll figure out everything else later. One of our insights is that this does not work well, and it considerably slows down the team right when it grows, especially presumably tasting success from the 0 to 1 stage. Even companies which are in the 1 to many stage sometimes lack important pieces of infrastructure, and this is a common pitfall that might be missed. To ensure success in the long term, we need to get both stages right. So the first stage is model development. This is where we develop a machine learning model that is solving the problem better than any other solution. So in the 0 to 1 stage, you want to put a lot of emphasis on the quality, data quality for features and labels. It is a must-have. For example, using historical features versus incorrectly snapshotted features might be a difference between a good and an average model. It is usually hard to get, so we have to invest early in a good offline infrastructure. It is very key for deriving reliable conclusions from offline experiments. Otherwise, a lot of effort spent in these offline experiments are not being tracked towards the goals. And lastly, like something very obvious but has to be said is that we want everything to be in Git. Data scientists usually tend to ignore Git, but it is very important to have a version control as part of our culture. This helps track even the vague ideas which are tested but fail, and usually people return to them unless we have documented them well. In the 1 to many phase, you should think of creating a rigorous framework for A/B testing and measuring the impact of different solutions. It is also time to double down on process standardization for the team. So one of the key insights we want to share here is the need for a feature label store from the start, especially if you have more than one data scientist working on it. This ensures that the features don't have an offline-online queue. It ensures that there is no diverging code base for offline-online features, and it simplifies data versioning. It also ensures that data scientists can work in parallel and can reuse each other's work. A lot of companies and a lot of use cases have stumbled upon because of the offline and online discrepancies in the features. The next stage is model deployment. This is where we have to deploy the model and make sure it is working as expected in production. In the 0 to 1 phase here, you want to define APIs in such a way that serving platform and ML models under the hood can be changed in the future. At this stage, you can get away without monitoring and observability. However, as you go to the 1 to many phase, the monitoring and observability becomes a must. You want to avoid silent failures in production at all costs. They are usually discovered very late, only when somebody accidentally stumbles on these. In the model deployment phase, we have built a model checklist where in 0 to 1 phase, you start with unit tests and integration tests. And as you go to 1 to many phase, you start monitoring model scores, features, and start looking at concept drift detection. The next stage is continuous improvement, where you work against entropy to ensure that your models don't become worse over time. This is the time in 0 to 1 phase, you want to set up CI/CD for model and data pipeline repositories. You need to introduce not only model, but also data versioning. Here, you can get away with simplified experiment tracking and no model registry. But soon in the one-to-many phase, you want to introduce continuous training of your models, especially the ones that deteriorate over time. You want to introduce experiment tracking platform and model registry as part of your ecosystem. This is also the time to aim at productivity so that you can test a new hypothesis and deploy the resulting changes within one day. One of the checklists we have built here is to think of which components should have CI/CD, that is continuous integration, continuous deployment or delivery. That includes data pipelines, models, data warehouse definition languages, feature definitions, and data quality checks. The next stage is model governance, where you standardize the access control, policy implementation, and activity tracking of models. In the 0 to 1 stage, this is a little light where you want to just make sure that you understand regulations of your specific use case. But pretty soon you want to invest in model health dashboards and monitor the model and feature drift. You also want to think of bias detection and responsible AI in this stage. Here is an example of a feature drift. Especially in fast-growing companies where the nature of our demand and supply evolves very quickly, or the distribution of your data changes very quickly, your models need to be on their toes to adjust to these changes. And the first step there is to monitor and know. It is also important to define monitoring on a deeper layer as you mature more. For example, while average statistics might look good, we might have large movements between the key subsegments of the clients. This is very similar to the Simpson's paradox, which you might be familiar with. This brings us to the last stage, which is the cost optimization. This is where you want to improve the value to cost ratio for your ML system. So in the 0 to 1 stage, you want to calculate and optimize the compute costs of the solution before the implementation. But as you become more mature, you want to start setting up alerts for costs. And especially if your team is big enough, you should consider open source solutions for the most costly parts of the infrastructure. So ML engineering overall, to summarize, is 10% ML and 90% engineering. And the engineering part is what we call MLOps. You can have the best data scientists on the planet, but without MLOps, you won't get the best business value out of their work. That brings me to the next question, like how can Turing help you in your journey? We have recognized 3 buckets of challenges which we have learned from our own experience as well as our clients. They are talent, workflows, and tools. When it comes to talent, not all data scientists are good engineers. So if you don't hire right, you might end up with a deep dependency between your engineering team and the data science team. And it creates a large overhead for both teams to plan and execute. It also, either team is not well equipped to operate independently on their respective ML ecosystem. The next challenge is workflows, where the teams usually comes up with fragmented process, which further strains the collaboration between data science and engineering. It also creates operational challenges for the engineering team for model management and deployment. And the last bucket is tools. There are a variety of tools and solutions for each component of the MLOps ecosystem. They are not always homogeneous, and choosing a wrong tool can be detrimental to scaling your ML capabilities at enterprise scale. So at Turing, we offer AI consultancy and delivery solutions to solve business problems at different levels of maturity. For clients who are just getting started, we work with them to create AI strategy. We identify a business problem, define metrics, and identify right tools and infrastructure technologies to solve the problem for them at enterprise-wide deployment. For customers who are a few steps ahead, we help build data infrastructure, implement data governance, and develop and deploy models for various applications, depending on the use case. And for someone who is already ahead, we help scale their AI models in cloud through AWS, Azure, or GCP, and we provide an end-to-end management framework, which includes development, deployment, and maintenance. So next, I'm going to talk about a few case studies from our clients. So this was a client who needed AI ML to help optimize their supply chain. They wanted to detect unusual partners in their supply chain and automate customer service experience. They also wanted us to help with their core problems of detection and prevention of disease, as well as accelerate productivity in surgical operations. So Turing implemented custom solutions for each of their 25 use cases and integrated them with the client's existing case management platform. With our help, we were able to drive 15% product recall efficiency, and we increased customer satisfaction by 6.4%. Similarly, we had another client who were a bit mature. They had an in-house AI team, and they still wanted to they leveraged Turing AI services to enhance their profitability. Turing helped them ingest new data sources and combine them with AI models to best determine prices and product bundles for the customer. We were able to drive a large increase in their product sales based on the power of AI. So that brings me to the end of my presentation. Please reach out with any questions in the Arize community Slack or email me. And you can visit turing.com/services.ai for more details. Thank you.